Welcome to the Unit 3 of Magnetic Effects of Magnetic Effects of Current and Magnetism, and we are dealing with the fourth chapter, Moving Charges and Magnetism. This is the second lecture for the fourth chapter. So till yesterday we covered about the relationship between the electric field and the magnetic force. Okay, we saw that how moving charge kind of reacts, or the effects that the moving charges feel due to an external magnetic field, and we also saw how you can represent the magnetic force that is experienced by such a moving charge. Okay, so by the end we also looked at Lorentz force and magnetic field. How do we describe it? So till the last the last part of it was a bit interrupted, so I will again revise it and then I will move on to the next parts. So what would be the motion of a charged particle when it is placed in a, say, uniform magnetic field? Okay, so this magnetic field is going inside the plane of the paper. Okay, as you can see in conventions that we had seen yesterday, we had seen that there are crosses on the plane. That means the field is going inside the paper. Okay, and you can see over here these are the charged particles. So we have seen that first of all that if we consider the velocity with which the particle is moving to be perpendicular to the field. Okay, so this and the velocity, the magnetic field and the velocity are perpendicular to each other. So the force, okay, so the force that is experienced by the charged particle is also perpendicular to the velocity and the magnetic field. So they all are perpendicular to each other. Okay, and the force then acts as a centripetal force, and the charged particle describes a circular path or a circular motion. Okay, if we have over here, since we are saying that the V is perpendicular to B, if there is a component of V which is parallel to the B, or it is along the direction of the magnetic field, okay, so this will remain unchanged. Okay, there will be no change in this component of the velocity that is along the magnetic field. Okay, but the field or the component of the vector which is perpendicular to the magnetic field, this is going to cause a helical motion of for the particle over here. So the particle follows a helical motion, okay, due to these two this perpendicular component of the velocity perpendicular to the magnetic field. Okay, so if you are considering again a circular path, the r is the radius of the circular path. Okay, over here also helical motion, also it's essentially a circular path, but it is also moving in the direction of the magnetic field. So r is the radius of the circular path. Okay, so the force that is acting on the particle can be given as mv square by r. Okay, so the force can be given as the mv square by r. Okay, and it acts perpendicular to the to the path, and it is directed towards the center of the circle. So this would be a centripetal force. And if the velocity v is perpendicular to the magnetic field, okay, the magnetic force is perpendicular to both v and b, and that again, as I said, it is going to be the centripetal force. So then there are different aspects of the motion of this charged particle when it is placed in the uniform magnetic field. Okay, so you have this first of all is a velocity, okay, and we also want to know what is the radius of the circular path that is being followed by the charged particle. So now we also know that force has this quantity, okay, qv by qvb. Okay, this we had seen in the last class. Okay, so if we equate these two sides, then what we can get is the radius of the circular path, and that is going to be dependent on the mass, velocity, and divided by the charge and the magnetic field. Okay, so this is the radius. Now if you want to find the angular frequency, okay, so that we can in terms of the velocity, it is v is equals to omega r. Okay, so omega will be is equals to v by r. So if you put the values of the r in this equation, 2 pi n, and also the value of v in this equation, you are going to be left with qv by m. Okay, so you can see that the angular frequency is independent of the velocity or the energy, but it is dependent on the charge of the particle and the magnetic field on which, which is acting on this particle, and the mass of the particle. Okay, so n over here is actually the frequency of the rotation. Now we are seeing that it's a circular path. Okay, so there would be some revolution, okay, that is followed by the charged particle. So to understand the time of that revolution, we can use the formula of t is equals to 2 pi by omega. So that equates to 1 by the velocity. Okay, if we have a component that is parallel to the magnetic field, it will make the particle move along the field. Okay, and the path of the particle would be a helical one. So that's what we said. If there is a particle which is along the field, and then there's a particle which is also, if there is a component of the particle of the velocity of the particle along the direction of the magnetic field, and there is a component perpendicular to the magnetic field. Okay, so the path that is followed by this charged particle is going to be the helical one. Okay, so now it's since how we calculated r for a circular path. Okay, so there is supposed to be some kind of distance traveled by the particle with respect to the helical one also. Okay, so the distance moved along the magnetic field in one rotation is called the pitch. Okay, so pitch can be given as a the product of the parallel component of the velocity multiplied by the time taken for one revolution. Okay, so if you put all your values of you have 2 pi by omega, so you put the value of omega, so what you are left with is 2 pi m v parallel by qb. Okay, so this v parallel is the value of the velocity, the parallel component of the velocity. Okay, so the radius of the circular component is called the radius of the helix. So this is how the motion of the charged particle actually moves when it is placed in a uniform magnetic field. So we understood the motion of a charged particle, okay, in a magnetic field. Now we will see what would be the charged particle in an external magnetic field. Okay, so now we will see what would be the motion in a combined electric and magnetic field. Okay, so previously we did not consider any electric field for this situation. Now we are going to consider both electric and magnetic fields. Okay. So first we will see the velocity selector. Okay, so why do we need a velocity selector? Why are we bothered about velocity? Because as we have seen that magnetic force is usually experienced only by moving charges or current carrying conductor. Okay, so now we are saying that a charge q is moving with a velocity v in the presence of both electric and magnetic fields. Okay, so if you remember, we had previously seen this in the last class, that the force, the equivalent force that is experienced by the charge would be sum of the electric field, vector sum of the electric field as well as the magnetic field. Okay, so we have the electric field over here. Okay, force is QE. Okay, and for magnetic force is going to be QVB. Okay, so we take the Q out as common and we add the electric field and the velocity into the magnetic field. Okay, now we will consider a simple case in which the electric and magnetic fields are perpendicular to each other. Okay, and perpendicular to the velocity of the particle too. So you can see over here that the electric field and the magnetic field are perpendicular to each other, as well as the perpendicular to the velocity of the particle. Okay, so with respect to this diagram, we can then assign vector unit vectors to all of these vector quantities. So the electrical force is equals to QE, that is QE then J vector. The magnetic force, sorry, this is the force due to the electric field, then the force due to the magnetic field is going to be QV cross V. Okay, and then you introduce your two other unit vectors, for one for the velocity and one for the magnetic field. Okay, and what you are left with is minus QVB, the unit vector. Okay, so if you put these two values back into this equation, what you are seeing is that the force is equals to Q in the brackets the electric field minus velocity and the magnetic field, product of velocity and magnetic field, and you multiply it with the unit vector. Okay, so this in itself we can see that there is a minus sign. Okay, over here also we saw a minus sign. This means that the direction of the forces that is caused due to the electric field and the magnetic field are opposite to each other. You can see over here that FE is pointing in the y direction and the FB is in the negative y direction. Okay, so now if we adjust the values of E and B, okay, so that is the field, that is the electric field and the magnetic field, we adjust the values so that the two forces are equal. Okay, then the total force on the charge is 0. If both the forces are equal, okay, so the total force is also going to be it's going to be 0. There is not going to be any change, and the charge will move in fields undeflected. Okay, so there will be no deflection, and this will happen as we said that the two fields, if they are equal. Okay, so then we can find the velocity, okay, at which the velocity at in the situation where you have equal electric field and magnetic field. Okay, so then V becomes a function of the electric field, the ratio of the electric field and the magnetic field. Okay, and the crossed electric and magnetic fields therefore serve as a velocity selector. Okay, so only particles with speed E by B, that is electric field by magnetic field, can pass undeflected through the region of crossed fields. Okay, so this is what we understand. This condition is usually, suppose we have a beam of charges which are moving at different speeds. Okay, so then using this equation we can use you can determine one velocity, okay, where it will pass undeflected. Okay, J.J. Thomson had used this method to measure the charge to mass ratio of an electron. Okay, so that is one of the uses of such a condition. Okay, and this is also used in mass spectrometer, where you can separate charged particles based on their charge to mass ratio. Okay, now we come to another example where you will see a combined effect of electric and magnetic fields. Okay, a combined effect of electric and magnetic field. The cyclotron is a machine that uses that usually uh, accelerates charged particles or ions, to high energies. So why, how do we do this? Is this again, we use both electric and magnetic field in combination to increase the energy of the charged particles. And we already know that usually electric field and magnetic field are perpendicular to each other, so they are also called crossed fields. Okay, and we have already seen how the frequency and the time of the revolution of a charged particle, it is independent of the energy. So this instrument can be used very well to accelerate the particles to increase their energies. So the particles move most of the time inside two. You can see over here that this is the construction or a schematic of the cyclotron device. Okay, so you have these two semicircular discs. Okay, metal containers, D1 and D2. They are called D because they resemble the letter D. Okay, there is a source of charged particles or ions at P. Okay, this is the P, this is the point where you have the source of the charged particles, and these move in a circular fashion, okay, in the D's D1 and D2, because we have a uniform perpendicular magnetic field. Over here you can see there are plenty of dots mentioned here, or represented here. These dots actually show that the magnetic field is coming out of the paper towards you. Okay, so this is a uniform uh, magnetic field. Okay, and the particle is traveling in a circular motion, in a circular pattern. Okay, and an alternating voltage source is used to accelerate these ions to high speeds. Okay, and when it reaches the this almost the edge of the container, it exits the cyclotron and it is collected, okay, over this part. This is where the deflection happens and then it goes out. Okay, so this is how the normal, how it works in general. Okay, so the particle is kind of shielded from the outside, and there is from the electric field that is present over here. But the magnetic field is acting on the particle, and that is why, as I said, that the particle moves in a circular path, as we have already seen. The sign of the field is changed alternately in tune of the circular motion. So what does this ensure? It will ensure that the particle always gets accelerated by the electric field. Okay. So each time the acceleration increases, the energy of the particle increases. And with the increase in the energy, the radius of the circular path increases. Okay, so that is why you can see that this is like a spire, okay, spiral path that is being followed by this charged particle within the cyclotron, within the two Ds. Positively charged particles, for example, protons can be released at this point, and they will move in a semicircular path in one of the Ds and arrive in the gap between the Ds, okay, in a time interval t by 2. Okay, so this t, as we have seen, we can give it as 2 pi m by qb. So Vc is the cyclotron, frequency over here. This is okay, mu c actually. This is going to be mu c. Yeah, this is a frequency of the cyclotron. Okay, cyclotron frequency. So we know that the inverse, the reciprocal of the time of the revolution gives you the frequency. Okay, so this is what we get, and with that we can get the frequency of the the path that is being followed by the particle. Okay, so that is going to be qb by 2 pi m. Okay, so the frequency is what we have found from here. Then suppose we also have a frequency of the applied voltage. We have seen that the voltage or the current, it is alternately changed. Okay, so it's an alternate current, so there needs to be a frequency of that too. So VA is the applied voltage. Okay, the frequency VA of the applied voltage is adjusted so that the polarity of the D's is reversed, and the same time that it takes the ions to complete one half of the revolution, that is to arrive in this gap. Okay, so there is a requirement of VA being equal to VC, and this is called the resonance condition. So the phase of the supply has to be adjusted. Okay, so when when the positive ions arrive at the edges of these two Ds, it needs to be at the low potential. Okay, and when it is changed, the ion need to be accelerated across this gap. Okay, and so it enters the next the other D. Okay, inside the Ds, the particles travel in a region free of the electric field. There is no electric field in this container and also in this container. Okay, so inside these Ds there is no electric field. Only in these gaps the electric field is experienced by the particle. Okay, and as soon as it reaches this gap, the phase of the supply is changed, which accelerates the particle and it moves into the other D. Okay, so there is an increase in the kinetic energy, which is equal to QV each time that it crosses from one D to another. Okay, so the V over here, it is the voltage. Okay, voltage that is there across the Ds at that time. So the ions are being repeatedly accelerated until they get the required energy to have a radius approximately that of the Ds. Okay, so when they have the radius that is approximately similar to the Ds, okay, it will kind of get deflected by the magnetic field. Okay, and that is when you try to understand what will be the velocity of that. Okay, so that velocity is given by QBR by M. Okay, and once they acquire this velocity, they get deflected by the magnetic field and leave the system by this exit slit. Okay, so R is the radius of the trajectory at the exit. So that is almost similar to the radius of the D's. So equals the radius of a D. Okay, so the kinetic energy then of the positively charged particle or ion is going to be half mv square, that is equals to the square of this. Okay, q square b square r square upon 2m. Okay, so this is what we find. So the operation of the cyclotron is thus based on the fact that the time for one revolution of an ion is independent of its speed or radius of its orbit. Okay, so the movement of the particle, okay, the way it takes up the circular path is not dependent on either its speed, the initial speed that it is orbiting, or the radius of the orbit. Both of them keep they do not have a role in this path that is followed. So that is why cyclotron is used to bombard nuclei with energetic particles. So when accelerated by it, they can result in nuclear reactions. Okay, they can also be used to implant ions into solids and modify their properties, or even we can materials. So usually cyclotron type of instruments are used in hospitals to produce radioactive substances which can be used in diagnosis and treatment. Okay, so this is how you can see that combining the effects of electric and magnetic fields, okay, all charged particles have a response to this combination. Okay, and usually the response is seen as the particles moving in a circular, circular path, okay, or a helical path. Over here you can see that in the same plane, okay, it follows the cyclotron, in the same plane it follows a spiral path. Okay, and due to like when we were considering the just a moving charged particle, you see that there's not much in change in the energy of the particle, but over here you can see that the particle is getting energized because of the effect of the electric current also. Okay, when we are only considering the magnetic field, the energization or increase or changes in acceleration is not happening, but for a cyclotron that is very much possible, and the entire principle of the working of the cyclotron depends on that. So now we will try to see uh, what would be the magnetic field due to a current element. Okay, so we have already just briefed upon in the introduction part that current itself can cause a magnetic field to occur. Okay, and now we will see that if we have current carrying wire. Okay, so we can see, we will try to understand how the current relates to the magnetic field. Okay, so we, as I said even before, that all magnetic fields that we know are due to currents or moving charges and due to intrinsic magnetic moments of particles. Okay, so even the substance that we are using, okay, it could be it has some intrinsic magnetic properties also, owing to the magnetic moments of the particles. So over here we will see the relation between current and the magnetic field that the current produces. Okay, and the law that we are going to understand over here is the Biot-Savart's law. So we are considering a finite conductor XY, okay, and it is carrying the current I. Now we will consider a small line element of dl, okay, and the magnetic field dB due to this element is what we need to find out at point P, okay, which is at a distance r from it. Okay, so we are going to consider this dl, okay, this line element, and we are going to consider, we want to understand what is the magnetic field due to this line element at the point P, which is at a distance r from the current carrying wire. Okay, theta is going to be the angle between the line element dl and the displacement vector. Okay, so since there is a magnetic field over here, so there would be some displacement also that is there. So there is a displacement vector r. So according to the Biot-Savart's law, the magnitude of the magnetic field dB is proportional to the current I, the element length dl, and inversely proportional to the square of the distance r. You can see again, even this kind of follows the principle of the inverse square law. Okay, so and its direction will be perpendicular to the plane that is containing the dl and r. Okay, so in vector notation we can write that the dB is proportional to I dl cross r upon rq. Okay, so this is what we understand. So the direction, if you remember in the last class we had understood the right hand screw rule. Okay, so if your if the current is being if the thumb of your right hand is pointing towards the direction of the current that is flowing, the fingers that are kind of rotating around that conductor, that kind of gives you the direction of the field. Okay, so over here you can see that the current is flowing like this. Okay, so if you wrap your hands around this current, so you can see that the field is going like this. Okay, so over here at this point it is going to look like it is going inside the paper, so you have the cross over here. Okay, at point P. If you have suppose another point over here Q, so at Q you can denote the field as a dot. okay, because of this right hand screw rule. Okay, so this is what we understand by the direction of the magnetic field. Now over here, since we said this is proportional, we need a constant of proportionality, so that can be given as mu 0 by 4 pi. Okay, so mu 0 by 4 pi, and then in normal notation you can write this as mu 0 by 4 pi IDL sine theta by r square. Okay, so when we take like the cross product, okay, if you want to uh, not use it in the vector for notation, you can write it as dl r sine theta. Okay, so then your r and this one r gets cancelled, so what you are left with is mu 0 by 4 pi IDL sine theta by r square. Okay, so this is again because it's a cross product. So this is the basic equation of for the magnetic field. Okay, so this is what Biot-Savart's law actually is based upon. Okay, so this equation is a representation of the Biot-Savart's law. Okay, so over here when we consider mu 0 by 4 pi, okay, so mu 0 is called the permeability of free space. If you remember in the electrostatics part, we had dealt with permittivity of free space, so that was epsilon 0. Now this is actually mu 0 is the permeability of free space. Okay, based on this equation we can then find that there are some similarities with respect to the Coulomb's law that we had defined for the electrostatics. Okay, we had already discussed this. Okay, so what are these similarities and differences? Okay, both are long range since both depend inversely on the square of the distance. If the square of the distance is it's smaller, your the field is going to vary accordingly according to that. Okay, so on the square of the distance from the source to the point of interest, if it is at an infinity, okay, so we don't really kind of we can see that there is not much effect, okay, if we consider a point at infinity. And we can also see that the principle of superposition is applying to both the fields. Okay, so with that we can say that the magnetic field is linear in the source. Okay, it is linear in the source IDL. Okay, this is together IDL, just as electrostatic force is linear in its source, the electric charge. Okay, so IDL, that is the the product of the current and the line element, or whatever we are considering the charge, okay, maybe moving charge also. So that is going to be the source. Okay, so the magnetic field is linear to this source, and electrostatic field is linear in its source, that is the electric charge. Okay, so now we can see that electrostatic field is produced by a scalar force, namely the electric charge. Okay, this is one difference between the magnetic field and the electric field. Okay, so the magnetic field is produced by a vector source IDL. Okay, and which is a vector source. Okay, so we saw that in this equation we saw that the magnetic field is a product of the current and the cross product between the line element and the distance between the line element and the point at which we are trying to find out the magnetic field. Okay, so this is a cross product, which is not the case when we were seeing in the electrostatics. Okay, so electrostatic field is produced by a scalar source. Okay, electric charge, it has no direction associated with the electric charge, but the magnetic field is a vector product, so it depends on the direction of the source. Okay, so we actually it depends on the direction of the current. Okay, as well. Okay, so it will depend on this, and it also depends on the the distance, that is displacement vector also. The electrostatic field is along the displacement vector joining the source and the field. Okay, the magnetic field in its in contrary is actually perpendicular to the plane containing the displacement vector r and the current element LdL. Okay, so we saw this over here when I explained the right hand screw rule. Okay, so this is the plane of the current as well as the displacement vector r. You can see that the crossover here denotes that the field is actually going through the plane. Okay, it is going through the plane away from the away from us, away from the observer over here. So it is perpendicular to the plane. And if you consider this point, so the field is coming towards us, okay, and through the plane over here, and so this is perpendicular to the plane which is containing the current as well as the displacement vector r. Okay, whereas in electrostatic field, if you remember that we were considering the for electrostatic field, suppose this was where we were considering the q plus charge. So the if we are considering this as a point, okay, so the electric field was usually directed along this distance r. Okay, so displacement vector r. So this is another major difference that is seen between electrostatic field and magnetic field. Also, we see that there is an angle dependence in the Biot-Savart law, which is not present in the electrostatic case. Okay, so magnetic field at any point in the direction of dl is 0. Along this line, you have theta is equals to 0, sine theta is equals to 0, and that is why the magnetic field would be 0. Okay, so this is the direction of the dl, okay, the line element. Okay, along this, as you see, this is the theta. Okay, so if your magnetic field is in the direction, okay, if your magnetic field is also parallel to this dl, the theta becomes 0, okay, and if sine theta, the theta is equals to 0, your sine theta will also be 0, okay, and that is why there would be no magnetic field at that time. Okay, so magnetic field at any point in the direction of the line element that we are considering of the current carrying wire will be 0. Okay, so this relation we can use to find the values of the the constant of proportionality or the permittivity and the permeability of the free space. So how do we find that? So if we take a product of the permittivity and the permeability of free space, so what would be that equal to? Okay, so that would be 4 pi epsilon 0, okay, in brackets, multiplied by mu 0 by 4 pi. Okay, so this is where we get, and then we try to get the values of it. If you remember, 1 by 4 pi epsilon 0 is equals to 9 into 10 raised to 9. Okay, we had seen this in electrostatics. Okay, so since we are considering 4 pi epsilon 0, we take the reciprocal of that, that is 1 upon 9 into 10 raised to 9. Okay, and over here we have already said that mu 0 by 4 pi is equals to 10 into minus 7, 10 raised to minus 7. So we multiply that over here, so 10 raised to minus 7. Okay, so what is that going to give us? So that is going to be 1. We are considering this is we kind of already subtract this. Okay, so that would be, we bring this down. Okay, so this becomes plus 7, so 9 plus 7, that is going to be 10 raised to 16. So we try to get it in the square form. So 3 into 10 raised to 8 by square. So now as we know, 3 into 10 raised to 8 is the speed of the light. Okay, so this then we can say is equal to 1 upon c square. So this is the equation of the permittivity, equation for the product of the permittivity of of the free space as well as the permeability of free space. Okay, so since the speed of light in vacuum is constant, okay, so this is also fixed in its magnitude. Okay, so if we choose either E0, sorry, epsilon 0 or mu 0, that is the permittivity or permeability, it will fix the other value of it will fix the value of the other term. Okay, in this equation we know this. Okay, we know the the value of the speed of light. So if we want to find permeability, we can fix one value for permittivity and vice versa. So this equation is also important for us, okay, when we are trying to calculate electrostatic field, okay, and magnetic field. Okay,